Okay, so in this video, let's understand what confidence intervals are. So let's say I have a sample, all right. Let's say the sample has 10 points, x1, x2, and x10 till x10. And let's say the sample is the heights of people, okay? So if we want to if we want to estimate the population parameters, let's say mu and variance, how do we do it? Well, we saw in the maximum likelihood estimation video that we can start with a belief about what the population distribution might be. And we know that the heights of people generally follows a Gaussian distribution. So we can assume that the population distribution for the sample is a Gaussian. And then using the MLE and everything we learned there, we can estimate the parameters of mu and sigma from the sample as the mean and standard deviation of the sample. So that gives us the maximum likelihood of finding the sample from a population with the same mean and standard deviation, right? But if you notice that, the heights of people, there are thousands and millions of people in a city, right? There are thousands of people in a city. So if you take 10 samples, you might get the mean for this sample as 168. If you take 10 different samples, you might get a mean of 170.2. If you take 10 different samples again, you might get 167.9, right? So what I'm trying to tell you is, when you use something like the MLE, you try to find a point estimate uh, for your population parameters, right? But if you see here, for different samples, you can have different estimates, right? You can have 168 as mean for this sample, which will in turn, if you use MLE, be the mean of the population as well. So what if instead of taking point estimates, I can find a range of estimates for the mean of the population, such that, I can say that the population mean mu belongs to a range of, let's say, 163 and 173 with uh with a confidence of 95%. I mean, if I say something like this, obviously it makes more sense, right? It's much more better than the point estimate that we saw over here. So that's what confidence intervals are all about. So they basically give you an interval in which you are most likely expected that the mean of the population will lie in. And this percentage, which is called the confidence, it's denoted by C. The confidence tells you the how confident or how high the probability is of you finding a mean in a particular range. In this case, the range is this 163 to 173. So that's what confidence intervals are all about. Yeah, so how do you compute a confidence interval? Well, if you know the underlying distribution is, let's say, Gaussian, if I know that my underlying distribution is Gaussian, I can, and the, if I know for sure that my underlying distribution is Gaussian, and if I have the sample mean and standard deviation, I can just say that, I know that within, if this is the mean, let's say this is the mean, and the mean of this sample is also 168, and the standard deviation of this sample is, let's say, the standard deviation is 5. So I know that 95% of my population will lie between two standard deviation, right? We know this from the properties of the Gaussian distribution: 68, 95, 99.7. So I know that 95% of my population will lie between two standard deviations. So if I know for sure that my underlying distribution is a Gaussian, which in the case of heights is very common, I can say that 95% of my population lies between the interval 163 and 173, because the mean of my sample is 168 and the standard deviation is 5. Right now, what if I don't know the underlying distribution. What if, let's say, this x, which is the samples x1, x2, all the way to x10. What if this comes from an entirely different uh, distribution, right? What do I do then? In that case, I can use the central limit theorem. We learned in one of the previous videos what the central limit theorem is. So what I can do is I know that my sample mean is going to follow a normal distribution from the central limit theorem. This is from the central limit theorem. I know that my sample mean is going to follow a normal distribution with the mean almost equivalent to the population mean, right? And the standard deviation equal to under root n, sigma by under root n. I know that my population mean, my sample is going to follow this. It's going to be normally distributed, right? So I can say that if I have to estimate the population mean, I can say the population mean basically is almost equal to x bar minus 2 by sigma under root n to x bar plus 2 sigma upon under root n, right? This is from the central limit theorem. If I know that my sample mean follows the population mean, I can say that the population mean is also equal to x, the sample mean plus or minus 2 sigma under root n. That's what we did over here, right? This is from the central limit theorem. Okay, this is case 1. This is case 1. Okay, when we know the population standard deviation, okay? We know the population standard deviation is available to us, but the mean is not. So we estimate the population mean from the sample mean using this central limit theorem. Now, what about case 2? What happens if we don't know the population standard deviation? Population standard deviation is unavailable. What happens in this case? In this case, we can just say that the sample mean follows a t distribution. A sample mean follows a t distribution with n minus 1 degrees of freedom. T distribution is again another distribution that's very closely related to the normal distribution, right? And so if we don't know the population standard deviation, we can just say that the sample mean follows a t distribution with n minus 1 degrees of freedom, where n is in this case is 10. It's the sample size, right? In our case, n is 10. So that was case 1 where the population standard deviation is known, and case 2 where it is not known. Now let's say just in a very now look here, what we've seen is we have seen how to how to estimate the mean and the standard deviation. But what if I want to estimate the confidence interval for other things, for other test statistics? Like what if I want the confidence interval for median, right? What if I want it for mode? What if I want it for, let's say, something like the 90th percentile? I can take the test statistic for anything. What if I want to find a lot of test statistics and I don't even know the underlying distribution of my of my population? I don't know the underlying distribution of my population. I don't have the mean. I don't have the standard deviation of my population. Mean and standard deviation of population is not available. Hell, I don't even know the underlying distribution of my population. So how do I go about doing this? I can use the MLE again, but again, it gives you point estimates and you're making an assumption that your distribution follows, the population distribution follows something. But what if I don't know any of this? All that I'm given is a set of data points, x1, x2, all the way to, let's increase the data set size over here to x30. Okay. That's all that I'm given. So what do I do now? Well, this is where we use something called confidence interval this is where we find the confidence interval using empirical bootstrapping. Empirical bootstrapping. We learned in one of the previous videos what bootstrapping is, right? So that's what we're going to apply here to find the confidence interval for anything, the mean, median, mode, or anything whatsoever. So what I'm going to do over here is I'm going to take I'm gonna take multiple samples from this sample. So I have 30 samples, and I'm gonna take multiple samples here of, say, let's say size 10. S1 is x1 of 1. The superscript over here tells me what sample I'm in. X1, x2 of 1, x3 of 1, all the way to x10 of 1. Sample 2 over here is x1 of 2, x2 of 2, all the way to x10 of 2. Similarly, I can take some m samples, okay? Sm is x1 of m, x2 of m, all the way to x10 of m, right? So I've taken some m samples with 10, with the sample size 10, which is less than this sample size. So what I'm doing here is I'm forming, and this is with replacement, okay? This is very important. This is with replacement because bootstrapping is always with replacement. So what we are doing over here is we are random sampling with replacement. Okay, so what I'm doing here is I'm coming with the belief that my entire population is just this sample X given to me. Okay, that is my belief that my entire population very closely resembles the sample that I'm given of 30 data points. Okay. Now, in case I want to find the median, okay, I want to find the population median. So for every sample that I have over here, I will take a median 1, then I'll take a median 2. I'll keep doing this all the way to median m. Okay. I have m medians, and this is my sampling distribution, right? This again is a random variable. And we saw from the central limit theorem video how this forms a sampling distribution. So all of these medians that I have, what I'm going to do next is I'm going to sort them in ascending order. In ascending order. Okay. So I'll have, when I sort them in ascending order, I will have my samples in some, I'll have my medians in ascending order. Let's say in ascending order, it's m1 dash less than m2 dash less than all the way to, let's say, m1000 dash. Okay. So let's say this m over here, this m over here is 1000. We have taken 1000 samples, each of sample size 10 from this sample of sample size 30. I hope you're understanding this. And now if I want to find the 95%, if I want to find the 95% confidence interval for my population parameter, what I'm going to do is I'm going to take all the medians between m-25 all the way to m-975. Okay, because the count of this is 950, and 950 upon 1000 gives me the 95th confidence interval for my population median, right? So this is what I'm going to do. I'm going to take all the medians between m-25 and m-975 arranged in ascending order, and I'm going to say that that is my population, that is my population median. Okay. And that my population median will fall in a range of medians from m-25 to m-975 with a 95% confidence. Okay, this is with a 95% confidence. So that's how you estimate using bootstrapping the population parameters like mean, median, mode, 90th percentile, whatever, when you don't know your underlying distribution, when you don't have the underlying distribution mean or the variance or the standard deviation, you just have some data points. Okay, this is very important. This is actually very widely used in numerical computation these days, because earlier when you didn't have computers, you couldn't use this a lot. But now that you have computers, you can take a very large sample size. This m can go on to 10,000, 100,000, or 1 million, whatever. And with computers, empirical bootstrapping is actually used in industry a lot. It's used in hedge funds, it's used in academia. This is very important. So yeah, I'll stop the video here. Thanks for watching.